Hello there, my name is Aidan, and today I'm going to introduce you to some work that we've been doing with polynomial eigenvalue decomposition, and actually using it for the task of broadband source localization, or in this case sound source localization. So why is sound source localization so important? Well, you can imagine even in our day-to-day lives we have things like smart devices. More and more robots need to understand their environment. So there's lots of different devices that need to be aware of where sounds are coming from, the angle of which they're coming from. And a subset of sound source localization is direction of arrival, which is the azimuth part, working out at which angle do sound sources arrive. And that's what this work is going to look at. And basically, how we're going to do that is we're going to look at how can we make the music algorithm, that's probably most of you will know, work with broadband signals. There's some current methods, but using polynomial eigenvalue decomposition is a slightly newer one. So let's consider our signal model first before we go any further. If we have a sound source, in this case this green S0, and a linear array, we can see here we have M microphones. As the sound propagates through the medium, it will hit microphone 1 first and microphone M last. So how do we capture that particular delay? Well, we do that through what is called a steering vector, which is this A0 that you see on the screen here. We multiply our sound source by the A0, and that will represent what we receive at this microphone array. And we can add multiple sound sources, so this one's at a different angle, so now it actually hits microphone M first, so we just have a different steering vector, A1, or we can go all the way up to R, and we can actually simplify this as just the sum of lots of sound sources multiplied their steering vectors gives us the output that we receive, or sorry, say the input that we receive at our microphone array. So how do we actually think about these steering vectors? Well, they should be real-time delays. So we see this blue signal here. This is implementing a real-time delay that could be fractional because you might not have an integer number of samples, convolved with our sound source, which is S of n. Now what music would normally do is say, rather than the signal x1 just being a delay, real-time delay convolved with S, what narrowband music says is we can collapse this down and represent it as just phase shifts. A simple example of that would be, imagine if you had a sine wave. If you were to delay that in time, that would be exactly the same as a phase shift. The problems arise is if you have broadband signals like speech, then obviously delaying something in time, the higher frequencies and the lower frequencies are going to have massively different phase shifts. So it no longer works. The trick that people normally use is, well, you can make this broadband problem of speech lots of narrowband problems. We can basically run narrowband music on independent frequency bins. So we frequency bin the speech signal, and then we run narrowband music on those frequency bins independently. The polynomial eigenvalue decomposition approach solves this problem as a broadband problem, and then it means that you can capture correlations between the frequency bins. They're no longer independent, which should mean that the performance is better. So how do we get there? Well, we first have to think about the signal model. We have a sound source S that's convolved with a room impulse response H with some additive noise. And then we need to use this to capture the spatial information. Now, normally in music, you wouldn't have a tau here. This tau would be 0, and we would get a covariance matrix. But in this case, we use this tau to introduce lags. And this lags will help us to capture temporal correlations. The cool thing about polynomial matrices and polynomial eigenvalue decomposition is that it can decorrelate spectrally, temporally, and spatially all at the same time. So normally we would just have a simple covariance matrix, which is just the outer product, and this tau wouldn't exist. And then we can only do it spatially. We can't do it temporally at the same time. But now by adding in this lag, using the polynomial approach, we can capture those temporal correlations. And that's why it's now called a space-time covariance matrix, because it captures both space and time together. So what would that look like? Well, you can see here we have some peaks, and on the diagonal we have the autocorrelation functions, and on the off diagonal we have the cross correlation functions. So this would be microphone 1 with microphone 2, microphone 1 with microphone 3, microphone 1 with microphone 4. And as you can see, the delay between microphone 1 and microphone 4, because this is a linear array, is much larger, and that's why the peak is shifted. So we can actually see just by looking sort of some of that spatial information. Now, if this was normal music, we would only see this 0 time lag, so these peaks at 0. And now you can imagine if you were to run EVD, which is the next step of the music algorithm, we would set this tau equals to 0 component to 0 on the off diagonals. But the problem is the peak is actually not at tau equals 0, it's shifted. So we can't actually access this information, we can't set it to 0, because it doesn't exist in the covariance matrix, it only exists in the space-time covariance matrix. So the cool thing about PVD, or polynomial eigenvalue decomposition, is it will set all of these off-diagonal components to 0 at all time lags. And we'll see that in just a second. And once we've done that, we can separate it out, just like normal EVD, into a signal plus noise subspace and a noise only subspace. So let's see that. And this is what we get. So we get basically a rank 1 matrix where we see most of the information, pretty much all the information is captured here, and then the noise is captured in these last 3 components. And all of the off diagonals are set to 0. So this is the eigenvalues of the polynomial eigenvalue decomposition, which is what we would expect. And now using that, we can use the same approach that we would use in music, which is we can use a broadband steering vector this time rather than a narrowband one. We can use our noise-only subspace and we can do a grid search of all possible angles of the steering vector, and we can find the angles that are orthogonal to the subspace. We can also threshold these eigenvalues to see how many sound sources we should be looking for. So in this case, we should be looking for 1. So we find the most orthogonal component, the angle that makes it most orthogonal to the noise subspace. The main reason why we wouldn't search the signal and noise subspace is because if we had multiple signals, which is what music stands for, multiple signal classification, then the multiple signals would have to be orthogonal with each other, which is why we make it an inverse problem and search the noise subspace or the noise only subspace. So that leads to what's called spatial spectral p-music, because it's decorrelating or finding out spatially and spectrally at the same time. And again, yes, we get this inverse problem. So this should look exactly the same as music. It's just now become broadband because we're using polynomial matrices, and we've changed the steering vector to be broadband. So some of the things that you need to do to make this work in practice on real sound sources or real speech signals is we first need to think about this steering vector. So how do we actually do these broadband steering vectors? Well, a simple way to realize them is to use a sampled sync function, but that would actually lead to an infinite impulse response. So we have to truncate that sync function. And it's been shown in the past that we should do that using a window. And in this work, we actually use a Hamming window. And you can see the difference in this diagram that windowing has. And to give you an example of one of these broadband steering vectors, if the reference microphone is microphone 1, then obviously no matter what the angle is, we'll get 0 delay. But as we go to the other microphones, you can see the delay gets more extreme at the extreme angles. So it's still 0 when the wave is coming face on because it hits all the microphones at the same time, but the microphone that's furthest away will get hit last. So that's why there's a greater delay for microphone 4 rather than microphone 2, for example. So that's what they look like in practice, these sync functions that have been windowed. A second one is we need to think about the temporal support that we allow. We don't have to allow an infinite amount of temporal support for the whole signal. In fact, we only want to capture the direct path. So if I go back to this particular picture here, we only want to capture these first peaks that represent the direct path. If we continue to make tau larger than 10, we might see some other peaks that represent early reflections if it wasn't in an anechoic environment. But the early reflections won't really help us in our sound source localization in this case. So since we know the array geometry in most cases, we can use that to inform the temporal support that we allow. So we look at the largest microphone pair and we look at the maximum delay that that's going to have, and then we can make sure that our temporal lag support includes that. So that's how we chose that value in the paper. And then finally, we only want to look at active regions. So first you want to use a VAD, so you're not looking at regions where there's no speech at all or no sound. And secondly, for speech, we only wanted to look at 100 Hertz to 4 kilohertz, because that's where most of the information will be. We don't want to go all the way up, past 10K. You're not going to see anything there, especially because we're using Locator, so the sampling frequency is at 48 kilohertz. So we have lots of information above 4K that probably is not going to help us very much. And you can see the difference here in this example. So you can see we're only going from 100 Hertz to 4K. But polynomial music, or spatial spectral polynomial music, you can see there's two distinct sound sources. But with normal narrowband music, this is using Acoustics, it almost looks like there's a single sound source with a reflection. So even though this red dotted line is slightly worse than this blue dotted line in absolute value, the actual dynamic range and the pseudospectrum is much better for SSP music, this polynomial music approach. So let's explore these results more thoroughly. First I need to define how we're going to explore them. So there's a couple of metrics. So a hit is when you detect a particular sound source within a collar. A miss is when you miss that sound source, you don't hit it in the collar. And then a false alarm is when you get basically you located a sound source that doesn't exist. And then the hit rate and false alarm rate are, as you would expect, sort of the relative values. The hits relative to the hits and misses, and the false alarms relative to the hits. So now we've got that in place. This is with some speech from Locator, and we changed using Acoustics. We rendered a 3D room, and then we changed the SNR values and the T60 values. So you can see here that when the SNR is high and the T60 is low, both algorithms perform quite well. But as the SNR goes down, especially below 0, we start to see at -10 it gets much worse, and at -15 normal music from Acoustics, this independent frequency bin music, starts to perform much worse than spatial spectral P music. That's because we think polynomial music should be more robust to noise, because it can decorrelate, again, spectrally and temporally, and it can capture correlations between frequency bins. So that's one example. If we have 2 sound sources, again, we get very good performance with 2 when the SNR is high. One thing I should say is you can see these results down here. Because they're slightly out of the collar, it means that when I show you the table at the end, it will look like when the SNR is high, polynomial music doesn't do well, but it's just because these results are just outside the collar, sadly. But as we can see, sort of anecdotally, if we go to a very low SNR value, normal independent frequency bin music is much worse than polynomial music. And that's what we see here. When the SNR is high, the reason this is lower is because I said that those results were just outside the collar. They're all about the same, but then as we go down to a lower SNR, you can see this blue solid line, which is polynomial music, is much higher than the dotted. And again, the green solid line is much higher than the dotted. Same is sort of true for reverberation, because you can capture these temporal components. So as we increase the reverberation, you can see that we get a few more spurious results with normal music. And then with a double sound source, again, the same thing happens as we increase the reverberation. You can see that we get more spurious results. Annoyingly, again, these are slightly off outside the collar, so that's why SSP music seems to perform worse overall at every level. But if you actually look at the graph, it's not doing that badly. But yeah, with a single sound source, it does much better, especially at high SNR values than the dotted line, which is normal music. And then just looking at Locator for some real data that hasn't been in a simulated room. And we wouldn't expect to do much better, because actually the noise and the reverberation is quite low. So there's very low noise, very low reverberation. But as you can see, we get very comparable performance. And especially in recording 3, we do much better than normal music, whereas the other 2, we only do marginally worse. And I just want to conclude then. So what we've done is we've talked about how we can develop and have explored this polynomial extension to music, which we're calling spectral P music, and why it might be advantageous to use it. We've also looked at some enhancements, things like windowing, making sure you look at the active regions and how you create this space-time covariance matrix and how much temporal support you want to add. And also we've demonstrated that actually SSP music is more robust to noise and reverberation because it can capture more information in the space-time covariance matrix. Anyway, thank you for listening, and if you do have any questions, please do email me. I'd love to hear from you, and yeah, hope you have a great day.